Yeah, thanks, Phyllis. Thanks, everyone, for being here. So I'll apologize in advance that I picked up a little bit of a cold over the weekend. So if that slows me down at all, then please be gentle, but I'll try and keep to time. Right, so the plan for today's talk is to talk about a few things we've worked out about the Random Walk Metropolis algorithm over the past couple of years, trying to get a very good qualitative idea of when it's going to work well, what features play into that, and how to sort of turn that into theorems eventually, right? So sort of a bit of intuition and then some understanding of how to make it more concrete. So all of this is joint work with Christoph, Anthony, and Andy. This sort of project began when Andy and I were both postdocs here in Bristol. Andy's since moved on to Warwick, where he continues to work on very interesting stuff. So the main references for this talk, so this big Poincare inequalities paper in the middle is the sort of tech report where we got started with a lot of these topics. I think it's mostly deprecated by now. The paper on the top left is where we study the Random Walk Metropolis in the sort of log concave setting, let's say. That's published in AAP as of last year. And then the paper in the top right is, it's about various things, various sort of related mathematical techniques, but it also includes the analysis of the Random Walk Metropolis in the case of heavy-tailed targets. And we're sort of revising that at the moment, and hopefully we'll have something new on archive within the month, let's say. Okay, so before getting into the Markov chain stuff, I want to give a bit of a background on this term isoperimetry, right? Because before I got into this project, it was something I'd not spent a terrible amount of time thinking about. And so I just want to give a bit of high-level intuition for what I mean when I say isoperimetry and how you should think about it, perhaps. So I'll give three sort of micro tasters of it to give some ideas. So right, the first one is the following. So this is something you might have seen, and if you did a maths degree, you might have seen this in first year undergraduate or maybe in high school if you were lucky. So this is a surface of revolution known either as Gabriel's horn or the trumpet of Torricelli. And so what you should think of this as, this is the curve y equals 1 over x for x greater than 1, let's say. And you rotate it around the x-axis to create a surface of revolution. Okay. And so usually when this is introduced to undergrads, the point of interest is that it's something where the volume that it encloses is finite. Okay, that's a nice exercise you can do, right? But the surface area is infinite. Okay, so there's an interesting, it seems maybe like a contradiction or a paradox or something like this, but it's something that's certainly true, right? And it's a bit surprising the first time you see it. So you have something where, the volume is small, but the surface area somehow is very, very big. And this is very surprising when you see it at first, but eventually when you reflect on the problem, you realize that this is kind of generic. It's not so hard to make something have big surface area and small volume if you want to fix it to be so, right? So this is something that maybe is a bit familiar as an example of an isoperimetric phenomenon where there's some relationship between, volume and surface area, which is a bit interesting. Okay, the second one is this sort of problem from antiquity known as Dido's problem. So the story goes that this princess had sort of been expelled from her kingdom and was looking to make a new start of things. And so she went to stay with a friend somewhere in the north of Africa, let's say. And looking to sort of set up a base, she said, okay, I've got this cow's hide with me, right? The skin of a cow. And I'm just going to, use it to enclose some area, and you can just give me that. You don't have to give me too much space, but just give me a bit of land to get started with, and then I'll be, building from now. And so the story goes that this Princess Dido, she did two very clever things. So one thing she did was she took this sort of two-dimensional cow's hide and carefully cut it into a very long string, essentially, turning a two-dimensional object into a one-dimensional object. And then she thought very carefully about how she could enclose the most area for herself to claim as much land as possible to sort of start her return to society, if you like. And so what she did was she arranged this string in this sort of circular arc that you see on the diagram here, which is, was nominally the basis for the city of Carthage, right? And so that was how she got on her way, was sort of carefully thinking about how to use a fixed perimeter to enclose a very large area. Okay, so it's sort of a similar story in that way, right? There are some sort of slight subtleties here with how you deal with the fact that the coast is not a straight line and so on, but that's not really the point of the talk, right? Okay, so a third story with a sort of artificial one. So think of the following. So say you have a sphere in 3 dimensions, and I tell you there's some sort of Brownian motion moving around on the surface of the sphere, right? And you can't control it or do anything about it. It's just going to carry on its way. And I say, okay, how do you cover, a part of the surface that has a given area such that the Brownian motion will spend as much time as possible in that area, right? That's a sort of occupation time problem, if you like. And so if you're someone who's thought about Markov chains a bit, you can say, this problem is not very interesting, right? Because if you fix the area, then by the sort of ergodicity of this Brownian motion, if you look at any set that has a given volume, the Brownian motion is going to spend about the same amount of time in that set as t goes to infinity, right? So there's nothing interesting to do there. But you can sort of enrich this problem a little bit. You can say, okay, well, let's say I want to put a set down where not only do I spend a lot of time in that set, but once I enter the set, I'm likely to stay there for a bit, right? So if I look at, I set some sort of time grid delta t or something like this, and I want it to be such that as often as possible, I'm in the set at time t, and I'm also in the set at time t plus delta t, right? So this is what I would call like a holding problem, sort of an extended occupation problem. Again, you're sort of fixing the mass of the set that you're allowed to pick, but you want it to be sort of well put together so that if you enter, you're likely to stay in it. And this one may be a bit less obvious, but this is actually in the same spirit as the previous two problems, right? That somehow, you want to pick a set that you'll stay inside, and that's a bit related to playing with the boundary of the set, and we'll sort of make that a bit more concrete later on. Okay, so those are some vignettes to give a taster for what isoperimetry might mean, right? Some sort of relationship between the bulk of a set and the boundary of a set. Okay, so now back to a more standard fare to motivate the study of the talk. So we're talking about Markov chain Monte Carlo today. And for the purposes of what I'm going to say, we're going to be thinking about sampling on a Euclidean space with a density with respect to a Lebesgue measure, which I'll call the target distribution throughout. Okay. Now the setup here, which I won't linger on too much, is the point is we want to take samples from this distribution to answer questions that are of interest to us, whether they might be statistical questions or scientific questions, theoretical questions, combinatorial questions, all sorts of things, right? And so the idea behind MTMC is somehow that we want these samples from pi. We don't think it's necessarily the best idea to try and come up with a miraculous one-shot simulator where you run a very clever program and you get a perfect sample at the end of it. But instead we use an iterative strategy, right? You take something that's, not a terribly good sample and you improve it a bit and you improve it a bit and you repeat this, n thousand times and you end up with something that you are happy with, which is an approximate sample, right? And so because these algorithms are not just thought experiments most of the time, they're algorithms we like to use in practice. A key thing is that we want them to converge in a small number of iterations so that we can go about our day and do other things, right? Okay, so and just as a schematic of what this would mean for us, so we generate some sequence of dependent points x0, x1, all the way up to some x capital N, with the hope that if we take this capital N large enough, then it has the distribution that we care about. And then once we have those samples, we use them to approximate integrals under pi and perhaps other things, right? So I won't really come back to this point too much in what follows, but it's just to set the scene, let's say. Okay, so in a way, the enterprise of MTMC, what I've described is very conceptual, but at some stage you need to come up with a rule for how to generate this sequence, right? And so there's many ways of doing so, and in a way, the whole field is thinking about very clever ways of going about this. And you can get very complicated or very simple depending on how you want to focus on things. And so there's one generic recipe for constructing kernels P, which are pi reversible, so a bit stronger than pi invariant, which is worth thinking about from my point of view. And it comes from the following way of thinking about things. So you have your distribution pi that you care about. Now you take some dominating measure nu, which is simple somehow. You can think of it as being an approximation, but it can even be a very crude approximation. It's just something that agrees that, these are the sets that have positive mass, let's say. So you start with some simple nu, and it's so simple that you already know some dynamics that would, leave nu reversible as well, okay? So there's some sort of basic exploration mechanism associated to this measure. And I'm going to write this var pi here for the density between pi and nu. And in what follows later, it will really just be the density of pi, okay? And so a Metropolis type algorithm is the following. So at your current state X, you propose a move according to this auxiliary kernel Q, where all we know about Q is that it leaves nu reversible. Okay, so that's sort of the basis for making little exploratory moves. Then we evaluate the sort of fitness of that move, if you like, by looking at the ratio of densities from X to Y, right? So if we move to a location of higher density, that seems natural to gravitate towards. We move towards an area of lower density, we might still go there for exploratory purposes, right? To sort of explore correctly. And so what we do is we compute this acceptance probability alpha, as written at the bottom here. And then with that probability, we make the move, in earnest. And with the remaining probability, we stay where we are. And that's what I would call a Metropolis type algorithm. It's a sort of strict subset of what people would call Metropolis Hastings algorithms, where your kernel Q can be a bit more general. But for me, a Metropolis algorithm, it's really where the Q is reversible with respect to something. And it may be something we don't even know. Okay, so this is a Metropolis type algorithm. So what's the schematic here? So up top, you have this sort of nice simple pair, nu and Q, that are reversible. And by sort of processing them appropriately with this density and this acceptance probability, we obtain a new kernel P, which is reversible with respect to this more complex measure pi that we actually care about. Okay. And this distinction of Metropolis kernel will come up a little bit later for a specific technical point, but I just wanted to precipitate that. Okay, so what's the specific version of this that we care about? Well, today it's the Random Walk Metropolis algorithm. And you can think of this as an instantiation of what I've just described, in the case where nu is the Lebesgue measure on RD, and this exploration kernel Q is sort of an additive Gaussian channel. You're at your current location, you sprinkle a little bit of Gaussian noise in each coordinate, and that's your proposal. And of course, that leaves the Lebesgue measure invariant. The fact that it's not a probability measure actually doesn't show up at all. Okay? So that's sort of useful. And so in this setting, we accept these moves with probability given by this formula here, where as you see, if the density goes up, then we accept the move for sure. If the density goes down, we consider it, right? And so throughout, I'm going to use RWM pi sigma squared to denote the Markov kernel that arises from this, right? So the target is pi, and the proposal variance, or somehow a step size, if you like, is this sigma squared, which is a non-negative real number, let's say. So this is a very old algorithm, a very widely used algorithm, and one reason for it is that it's very basic. All you need to do, in a way, to implement this algorithm is you need to be able to evaluate ratios of pi at different locations, right? And you need to be able to sample from a Gaussian distribution. And somehow, if you can't sample from a Gaussian distribution, you're maybe not in the business of Monte Carlo already. And this requirement of having pi up to a constant is pretty conventional for us. So I won't linger on that too much. Okay, so this is an algorithm. What can we say about it at a first pass, even just qualitatively? So under almost no conditions, basically the conditions that allow me to actually implement the algorithm, you will get a pi reversible Markov kernel out of this, okay? So you leave it invariant. If you start at the target and you run this Markov chain, you don't make things worse. Now the early things that were proven about this algorithm are sort of more qualitative than quantitative. And so the sort of results you might have would be the following. So under very mild conditions on the density, you will get an ergodic Markov chain, where as this capital N goes to infinity, you do really converge in distribution to the thing that you care about. Okay, so it's sort of fit for purpose, at least in principle. Now, if you want exponential ergodicity, so to converge at a rate that is exponentially fast, which is the best we can hope for in general, although we'll see some sort of caveats to that. Roughly speaking, if you have well-behaved tails which decay at least as fast as exponentially, then the Random Walk Metropolis will inherit that and also converge at an exponential rate. Okay, so that's a qualitative result, where if you look at those proofs and you try to get a quantitative rate out of it, you might struggle. But at least we know that it happens with some exponential rate there. Now on the flip side, we know that this is kind of the hard boundary, that actually if you have tails that are heavier than exponential, right, think of polynomial or sort of quasi-exponential things, then you're necessarily going to be slower than exponentially ergodic. You will still converge eventually, but the rate cannot be exponential. So this is useful, not so much in terms of getting mixing time results directly, let's say, but in terms of understanding what we can expect to prove even in principle. Okay, it sort of sets some nice boundaries for us. to give a quick bit of intuition on the heavy-tailed case, roughly the idea is, for heavy-tailed measures, there is quite a lot of mass in the tails. So to mix, you have to get out into the tails and then come back into the bulk and so on. And the random walk metropolis moves quite slowly. At each step, you move order 1 or order sigma, if you like. And you don't get out into the tails and back into the bulk quickly enough to have an exponential rate. That's sort of a heuristic argument. You don't see the tails rapidly enough. Okay, so what can we do to work towards some more quantitative results? So a natural thing to do when studying sort of discretized algorithms is to think about continuous limits that might be more convenient to study, right, to get sort of heuristics out. And so here, what we can do is we can take this sort of random walk metropolis algorithm and think about what happens as I send the step size to 0. And I'm not scaling anything else. There's no sort of products or optimal scaling type stuff. I'm really just sending the step size to 0, and I'm rescaling time diffusively so that we get order 1 motion on order 1 time scales. Okay, and so if you do this, you get that the sort of limiting process is this very well studied diffusion process, which is known as the overdamped Langevin diffusion, or I'll write it as OLD of pi. Okay, so we have that in some small moves limit, that's what we look like. And we would like to somehow say, okay, can we inherit the convergence behavior of this continuous process for our algorithm as implemented? And because we rescale time by sigma squared, quantitatively, we would hope to say, for suitable sigma greater than 0, we might like that the mixing time of the random walk metropolis algorithm is bounded above by the mixing time of this diffusion process scaled by 1 over sigma squared. That's kind of what we would like this to deliver us. Okay, so what is this diffusion process? So it will be convenient for us to write the target in this sort of statistical mechanical form where we center the sort of potential u, this function that's the negative log density, and we write the diffusion in this form with the minus grad u. So it's sort of a noisy gradient flow, if you like. And so if you're sort of mildly well equipped to do stochastic calculus and this sort of a thing, it's relatively straightforward to check that this gives you a process that is reversible with respect to pi, hence leaves pi invariant. Okay, and we expect it to be ergodic if things are sensible and so on. Now, in principle, this could be a sort of arbitrary way of sampling from pi. Many people in the audience will find it easy to come up with different examples of processes that leave pi invariant. But this is somehow a canonical process for continuous dynamics and sort of doing analysis with. So if you want to study sort of probabilistic aspects of geometry, things like concentration of measure and optimal transport, this is somehow a special process which tells you a lot of information about pi, right? And so the crucial thing there is that it's been studied extensively and many things are really very well understood by now. So it's if we can actually reduce the random walk metropolis to studying this diffusion process, we have a wealth of literature that we can draw on to understand the fine properties and so on. And we'll see that we can sort of deliver on that to some extent. Okay, so here's a crash course on what is true about the Langevin diffusion. Okay, so these are the things that, if you want to sort of prove your standard theory about MCMC algorithms in the nice setting, these are the things that are worth knowing. I'll just preface, for the more technically minded people here, when I'm talking about convergence, I'm talking about convergence in an L2 sense or in the chi-squared divergence and this sort of a thing. I won't get into the details of that for the most part. The point I would make basically is that it's quite a strong form of convergence, which implies things like convergence in total variation, convergence in sort of other divergences as well. So it's a reasonably demanding way of imposing convergence. Okay, so what's true? So if your potential is convex, then you always have exponentially fast convergence. Okay, so this is sort of related to having thinner than exponential tails in a way. So that's good. That's a non-quantitative result as written, but it can sort of be made quantitative. That's basically a result of Bobkov from the end of the 20th century. Now, if you have your potential U is uniformly convex, which is to say that its Hessian is always strictly positive definite, and the minimum eigenvalue is bounded uniformly away from 0, then actually you have this interesting phenomenon where you are exponentially convergent, but at the start, when you're very far from equilibrium, in some sense you're converging at a faster than exponential rate. And this sort of reflects that when you're out in the tails, you get out of them very, very quickly, right? It's related to things that people would call sort of hypercontractivity and so on. Conversely, if you have a potential that grows sublinearly, so something like, the norm of x to 1/2 or the log of the norm of x, this sort of a thing, we similarly see that the convergence has to be slower than exponential. Okay, you have heavy tails, you can't converge as rapidly. Again, this argument that you don't see the tails rapidly enough holds water. There's an additional point which I think is worth making, which is related to some very exciting developments in convex geometry from the past 5-10 years in particular. So there's a conjecture known as the Cannon-Lovász-Monovitz conjecture, which says that if you have a potential U which is just convex, not strongly or anything like this, just convex, and you sort of fixed your coordinate system so that pi has covariance matrix equal to the identity. Right? So you do a change of coordinates so that everything is isotropic and so on. Then uniformly over that class of targets, the rate of convergence of this diffusion doesn't depend on anything. Right? It's bounded uniformly in dimension, uniformly in target, bounded below by some constant. And what that essentially says is if you're doing log concave sampling, and you're initialized well, and everything is scaled properly, there's no obstruction to converging quickly, right? So that's sort of, in a way, it gets at the core of why the log concave setting is quite so nice. Okay? So those are good for building intuition. And, okay, a natural critique here is that you have things that are, very strongly shape constrained, if you like, very convex in very quantitative ways. It's worth mentioning that there are various useful transfer principles that let you go beyond this, right? So if I start with something which is strongly log concave, and then I multiply its density by something that's bounded between 1/2 and 2, something like this, then the diffusion will do just fine on that target, right? Modulo the smoothness and so on. So that's sort of the bounded change of measure, or what technically people would call the Holly-Struck argument, from something from the early 90s. Similarly, if you can express your target measure as a Lipschitz transport of a nice measure, right? So you could obtain it as, if you compute the optimal transport map, for example, from the standard Gaussian onto your measure of interest, and it has a nice Lipschitz constant, then from the point of view of this diffusion, it's sort of as nice as the Gaussian would be, modulo a factor of that Lipschitz constant. Okay, so the point is, these first points 1, 2, and 4 let you prove nice things in these very nice cases, and then by fiddling around with these other principles, you can prove more general results. Okay. So let's try to get back to the random walk metropolis. So there's clearly, I've given this scaling argument. There's some strong resemblance between the two processes, between the random walk metropolis and the overdamped Langevin diffusion. And qualitatively, we might expect that if our acceptance rates are behaving sensibly, we're sort of accepting 1/4 of the moves that we make or something like this, because we haven't chosen a stupidly large step size, then things should be more or less the same, right? That qualitatively we'll get the best of this small sigma behavior. But it's quite challenging to make this rigorous because there's various forms of resemblance that you might choose to focus on, right? And a natural one, if you come from a sort of analysis or numerical analysis background, would maybe be to focus on pathwise behavior and say, okay, maybe I can try couple the diffusion to the random walk metropolis so that they move very close to one another for all times. Okay, that would be a natural strategy. My understanding is that this strategy doesn't really work because the resemblance is not true in a very uniform sense. Basically, when you're far out in the tails, right, of a Gaussian, for example, the diffusion process is zooming in at this exponential rate, and whereas random walk metropolis is just puttering along, adding a little bit of Gaussian noise at each step, right? So the approximation error is very non-uniform, and that makes it kind of challenging to enact this argument. This is to be contrasted with things like the unadjusted Langevin algorithm, where things kind of, it's much more plausible that things look uniformly similar, let's say. Nevertheless, what we will see is that they are quite similar in terms of what I would call exit behavior or boundary behavior, in the sense that if you look at each process and you say, how difficult is it for them to get into a set and then get back out of that set, right? So that's a much more large scale property that doesn't care about what happens, in terms of exactly how they get out, as long as they take about the same amount of time to get out, let's say. And we'll elaborate on that shortly. Okay, so the point is, okay, you can make the argument that these two processes look similar to one another, but at some stage you need to clarify the way in which they look similar to one another and why that similarity implies that they should equilibrate in a similar way. Okay, okay, so now we move back to the world of isoperimetry. So here I have to introduce a couple of definitions. Fortunately, they're very visual, so the geometric side of things should make it a bit easier to get a handle on things, but it is a bit new, and it was new to me. Okay, so this diagram sort of precipitates what I'm going to talk about. So the probabilistic picture of isoperimetry is the following. So fix the probability measure pi that you care about, and then think about some measurable set in RD, right? Something sort of reasonably well behaved. Call that set A, and now I'm going to define the R enlargement of that set to be all points that are within a distance at most R of that set. So some people will call this like the epsilon fattening or something like this, right? And so if I go back to this picture on the previous slide, somehow if you think of the interior of this blue set as being A, then the interior of this red set is somehow the enlargement, right? You're looking at all of the points that you can reach, from which you can reach the blue set within a move of, order 1, where 1 is the radius of this ball. Okay, so it's clear that by taking R positive, you have a bigger set, right? You enlarge the set, you enlarge its volume. And so it's interesting to ask how much does the volume of the set increase by, particularly when R is very small, right? And in various settings, you can make a nice argument that the sort of additional volume added on by the R enlargement should be approximately linear in R, okay? And so if you sort of take the derivative of this as R goes to 0, you obtain what's called the Minkowski content of the set A under the probability measure pi. And you can think of it as a sort of boundary mass or a boundary measure, right? It's how big is the boundary of this set as measured by pi and sort of the metric we attach to it, right? And so this is where we get back into the isoperimetry. We're interested in the boundaries of sets and how they map on to the size of sets themselves, okay? And so here's the next definition, which is a bit more challenging in some ways. So focus, throughout just focus on sets that are small, not with more mass more than a half, let's say. And so let I be the function such that if you look at a set that has mass p, you know that its boundary must be at least I of p, okay? So we're saying amongst all sets of a given mass, the one with the smallest boundary has boundary I of p. So this is what's called the isoperimetric profile of pi. Now this is in specific instances, this is a challenging thing to get your hands on, but if you do get it, you learn really quite a lot about pi, right? Yeah, and so as I write here, the idea is that you tend to use it as follows. If the mass of the set is p, then its boundary is at least I of p, right? And that's the isoperimetric property somehow. Because we're thinking of the mass as fixed and optimizing the boundary. Of course, you can invert things, right? To say, if I have a certain boundary mass, how big or small can I make the volume that it contains? A sort of challenging exercise, which is nice to have stewing in your mind a bit, is, okay, that if I fix the mass p, there's going to be some set A which saturates this inequality, right? Amongst all sets that have mass p, which one has the smallest boundary? It's a nice exercise to think about what the solution is. I'll sort of comment on that momentarily. But okay, so these are some sort of key definitions for what's going to come later. But the main thing is that this function I pi, it relates the mass of sets under P and their boundary mass, okay? And we'll see why that's relevant for Markov chains shortly. So let's give some examples to make it a bit more concrete. Okay, so let's just focus on dimension 1 for now, and we'll sort of touch on higher dimensions momentarily. So let's focus on the light-tailed case. First example, we look at the so-called Laplace distribution, where the potential is just the absolute value of x, so sort of this double-tailed exponential. In this case, the isoperimetric profile is linear. So what this says is if you look at any set, then you compute its mass under the exponential distribution, then the boundary mass of that set, which is just going to be the density of that set at the endpoints, that's not too difficult to show, is at least as big as the set itself, right? So the boundary is comparable to the mass itself, and so we get an isoperimetric profile that is linear in P. Okay? Now, if we move to the Gaussian setting in the second line, we get a bit more than that, actually. So we get that, this log 1 over P, it's at least a constant, let's say, because P is between 0 and a half. So it's true that the mass of the boundary is always at least as big as the mass of the set itself. But actually, we see that as P goes to 0, as we look at very, very small sets, they actually have conspicuously large boundary, okay? And you can think of this as relating to the idea that if you have light tails, if you condition on something being very large, the most likely way for it to be large is for it to be, slightly above that threshold, is what you would see in large deviations and stuff like this, right? And so, yeah, the key thing here is that for very small sets, you have sort of relatively large boundaries in comparison. And of course, it's not particularly surprising that if you look at x to the alpha type potentials, where alpha is at least 1, can be bigger than 2 also. that this trend continues somehow. As the tails get lighter and lighter, the isoperimetric properties of small sets get better and better, okay? And so what's nice is, because all of these examples are log concave, there are some very nice arguments that even though what I've said is in the context of one-dimensional measures, if I take product measures made out of these guys, the same is true, actually, that they will have isoperimetric profiles bounded in the same way independently of the dimension. And this sort of makes sense in the Gaussian case, right? Because you can imagine that whatever's happening for a Gaussian in high dimensions, the extremal sets might just be to do with one-dimensional projection, something like that. I won't talk about that in great detail. But okay, so the key thing here is we're in the log concave setting. If we're sort of just barely log concave, like in the Laplace case, we have this linear isoperimetry. But as soon as we get a bit better in terms of the convexity properties, the behavior for small sets can be much better, right? You can have small sets with big boundaries. We're going to see that for Markov chains, that's very useful for us. Okay, now some examples in the heavy-tailed setting. So for the first two lines, think of alpha as being something between 0 and 1, right? So we're looking at targets that are not quite log concave, but are, you know, still sort of exponentially decaying mass out of the tail at some rate. And so in the first line, in the sort of product of quasi-exponentials, we see that the isoperimetric profile has a similar character to before, but we see two new things. Number one, the dimension pops up, right? Roughly what this reflects is that as you take products of non-log concave things, the measure itself gets nastier and nastier somehow. You're sort of putting new obstructions into the problem. The other thing you should note here is that this 1 minus 1 over alpha is actually negative, okay, because alpha is less than 1. And so we're seeing that things are worse than in the exponential case. This is not just a relic of the product form setting. So if we look at the second line and we take a spherically symmetric model where the tails are decaying at this rate, you know, we get this p log 1 over p to the 1 minus 1 over alpha again, but we'll pick up some dimensional factors in there again. So that's a bit harder to make explicit, but again, you see that the dimension is making things worse and worse. In these last two examples, so these are sort of polynomial tails, sort of symmetric Pareto distributions, if you like. You see that you pay the price of dimension even more keenly, right? You're losing a polynomial factor out the front. You can have sort of very weird sets that, you know, essentially what's happening for heavy-tailed targets is out in the tails, you can have quite a lot of mass. Things are very flat, and the boundaries are not very big. Okay, and you know this happens also in the spherically symmetric case. The key takeaway here is that for bad targets, in the sense of being heavy-tailed, the behavior for small sets can really be quite bad. Okay, and we will see that that punishes us when we study the convergence of the Markov chain. And moreover, to contrast with the convex case, taking products of non-log concave things makes things worse and worse, right? Okay, but these are some nice model problems to get a bit of intuition. Okay, so I've given you some examples of isoperimetric profiles now. Let's talk a little bit about the maths that goes into proving these, because I didn't prove these from scratch, right? I sort of got these elsewhere. And so to give a bit of an idea of how one goes about this, so in one dimension, the picture is really very complete. Like with a bit of symmetry assumptions and some shape considerations, there's a really nice monograph from 1997 of Bob and Hudre that really, you know, gets a complete understanding of this problem with very explicit isoperimetric profiles. So if you have one-dimensional problems that are sort of reasonably well behaved, you can get very explicit answers there. For a slightly more general setting, so in the sort of mid-2000s, there was a nice line of work by some French and Chinese mathematicians on using sort of what people would recognize as drift type or Lyapunov type conditions on Markov chains to prove these isoperimetric estimates. Okay, and there's some sort of very nice mathematical techniques there. What I will say is these tend to be a good way of getting isoperimetric profiles with the right dependence on P, right? So how things behave for small sets. But if you care about the dimension dependence, you usually give something up. It's not necessarily terrible in the way that one would classically expect the sort of drift and minorization type proofs, but you tend not to get sharp estimates in this case in terms of the dimension dependence. Yeah, and Patrick Catio and Arno Gulan are sort of the experts on this. If you really want to learn this stuff, that's where I would start. As I mentioned before, you know, for many of these properties, if you have some sort of nice relationship with a measure where you have proved something already, whether it's a change of measure or a transport argument, you can often inherit this good behavior. You know, if something is not so different from a Gaussian in terms of density or transport, then it will have isoperimetric behavior much like a Gaussian. Moreover, under sort of convexity assumptions, we have this tensorization properties, right? That products of log concave measures are sort of as good as the worst one in the product. This is kind of what you would expect. Moreover, if you have sort of convex potentials, there's a very tight relationship between isoperimetric profiles and functional inequalities. So some people in the audience may have heard of things like Poincare inequalities or log-Sobolev inequalities. In general, these are not sort of isoperimetric in character, right? They sort of refer to something a little bit different. But if you have convexity assumptions, they are genuinely sort of quantitatively equivalent to one another. So that can be another nice way of getting a handle on things. Okay, so let me drink for a second. So a slightly peculiar thing about the isoperimetric profile is that the definition is very static, right? It's here's a set, relate its boundary to its mass, or here's a constraint on the boundary, find a good set. It's a very sort of calculus of variations type thing. What's very fortunate for people like me is that you can also think about it in a dynamical way. That this sort of notion of boundary is actually dynamic in some sense. And so consider the following thought experiment. So let A be some nice measurable set, right? Now draw a sample from pi restricted to that set. Okay, so you start at equilibrium in that local sense, and you evolve according to the overdamped Langevin diffusion. So you might leave the set, right? And so you could look at the behavior of the probability that you leave the set, given that you start in there, over a very short period of time, okay? And so you can think intuitively what's going to happen. I'm doing a diffusion over a very short period of time. I won't really see the drift, right? The diffusion term is going to be what dominates. And so for me to leave the set, what needs to happen is that I'm right near the boundary of the set, and then the Brownian motion kicks me over the edge, right? And so in this sense, right, the isoperimetric problem is actually a statement about how difficult it is for a Markov process to leave given sets and come back in, right? It characterizes the difficulty of a diffusion in this case to escape a set. Okay, and that's going to be useful for us in terms of studying mixing time. And so taking that intuition and pushing it into a functional form, and I won't give these details here, but I'm happy to talk about it afterwards if people can. So under quite reasonable conditions on pi, these are really sort of smoothness type things, you can bound the epsilon mixing time of the diffusion process in terms of this integral here, right? And so the integrand here is sort of depending like 1 over I squared on the isoperimetric profile. So we'll see that if you have a big isoperimetric profile and sets have big boundaries, then the mixing time is small, right? That's sort of what we would expect. And there's a dependence on exactly the threshold epsilon you want in the lower bound there. So you see that if you want very high accuracy samples, it's going to depend on the behavior of I of p for very small p. Okay, and this factor delta naught relates to the initialization. I will touch on it a little bit later. What's nice about this formula is that it gives a unified description for what happens in both the case where the process is converging exponentially, faster than exponentially, or slower than exponentially. It all just comes down to what this function I of p looks like. So when I said the isoperimetric profile includes a lot of information about the target, this is sort of what I'm getting at. Like it tells you, how fast you convert at the start, in the middle, and at the end somehow. Yeah, and you should note that the key thing from this somehow is that, the rate is dictated by how things behave for a very small p. You care about how difficult it is to escape very small sets, since those are the ones that will eventually trap you. Okay, so let's try bring this back to the Random Walk Metropolis, which after all is what I'm here to talk about. Right, so we've seen that using this isoperimetric point of view, we can get very accurate answers to what's happening for the overdamped Langevin diffusion. And so it's natural to ask whether it can also be informative about the Random Walk Metropolis algorithm. And so to first order, the answer is it can't tell us everything, right? Because the Random Walk Metropolis algorithm has this sort of quite fundamentally discrete character, particularly when you have very large step sizes, right? You sort of get very much band limited by trying to make very big moves and rejecting them all of the time, right? So whatever analysis we do, it will need to somehow pick out that for very large sigma, stupid things happen. But when sigma is small enough, life behaves well, right? But we'll see from the analysis that this is really the only extra obstacle that comes in moving from continuous to discrete. Okay, once we can handle sort of how these acceptances are taking place, we can really inherit the nice properties of the diffusion down to this Markov chain. And so the extra ingredient is this condition here, which we've inherited from previous works, mostly from the TCS community, I would say. So let delta greater than 0 be some sort of characteristic distance or length scale, let's say. And let tau be a threshold parameter between 0 and 1. You should really think of it as being about a constant, something like a quarter is fine, right? And so we're going to say that a Markov kernel P is delta Tor close coupling if the following holds. Once I get two Markov chains within a distance delta of one another, the total variation distance between the kernels starting from those points is bounded away from one, right? And it means that I can couple those kernels so that in one step, the two chains coalesce with a decent probability, okay? So this is really like a smoothness or a continuity condition. It's not a contraction. It's not a for all Tor there exists delta sort of thing. It just says, you know, your kernel is reasonably well behaved so that when you get close enough, two things can meet, right? And so this delta, you should think of it as being on the order of the step size, right? Yeah, and operationally, this is it, is that if we get our two chains within the distance delta of one another, we can make coalescence happen with a good probability. Okay. There are some very edge cases where you would want to think of very small Tor, but it really, most of the time, is just a constant. Okay. And so with this condition, this is what lets us bridge from the isoperimetric profile to this Markov chain P. Okay, so here's a proposition, which is a bit more general than just the random walk metropolis. So let our target distribution have an isoperimetric profile that we can estimate. Let P be a Markov kernel, which is high reversible and also sort of spectrally positive, I would call it, or positive semi-definite. This is not a difficult thing to enforce once you're reversible. And assume that this kernel is delta Tor close coupling in that sense, right? Then the mixing time for this kernel to reach equilibrium pi is exactly bounded above by this integral which we saw for the overdamped Langevin diffusion, rescaled diffusively by this delta times Tor factor, right? And I've suppressed the constants here, but in the papers you will find them, and real numbers, you know, they're things you can write down. Right, you should think, okay, in a way, what we're saying is my process is mixing as well as the overdamped Langevin diffusion, slowed down by delta times Tor squared. Morally, the squared there is again for sort of diffusive scaling, you know. Okay, so that's nice. That's a general result, and we're going to try show that this holds for the random walk metropolis. We've got to show this delta Tor close coupling condition. And so let's see what that looks like for us, and what specific things can we use that will make our life easier here. So we want to show that if I have X and Y close to one another, the metropolis kernels from those points are bounded in total variations, right? And so the following is a nice argument, which holds for any metropolis kernel. So anything where, you know, our proposal is reversible with respect to something. In any of those cases, it's true that the total variation distance between the metropolized kernels can be bounded by the total variation distance between the proposals plus the worst case rejection rate out of any state. Okay, the argument here is a little bit like, you know, okay, if I want the metropolis kernels to meet, what I should do is make them propose the same thing and then accept at the same time. That's, you know, algorithmically, that's what you would do somehow. And mathematically, it works out nicely too. This result is not true for general metropolis Hastings kernels. You really use the specific metropolis structure here. It's a very nice, more or less elementary argument that Anthony came up with, and I'm a big fan of. Okay, so if we can control the worst case rejection rate, we're in good shape, because controlling this total variation distance between the proposals is very easy. It doesn't depend on the target, really, right? So if I look at the total variation distance between two isotropic Gaussians with different means, I can use something like Pinsker's inequality and come up with a very nice bound on the total variation distance stuff. And so what we see from that is that it will be sufficient for us to upper bound the worst case rejection rate, or equivalently to lower bound the worst case acceptance rate out of any given state. And then we will have our close coupling condition, and we can inherit everything that we'd like from the diffusion process. Okay. So how are we going to do that? Well, let's look at what this worst case acceptance rate looks like. So this is the object that we care about. So fix a state X. The acceptance rate out of X is this alpha of X here, which is the average acceptance rate to any point that you propose from that. Okay. And written in this potential form, it has this very nice form where it's the expectation of the exponential in the change of energies, change of potential, but only looking at the positive part. Okay, this is sort of the min1 blah that you see in a metropolis method. So we want to lower bound this quantity away from zero uniformly in X, right? We want to show that on a typical proposal, the energy doesn't go up a crazy amount. And so it's natural to make some sort of quantitative smoothness assumption on U here, right? That's sort of very natural. And so here's a very general version. You know, we write more specific things in other cases, but assume that there's some symmetric function psi, or C I should say, such that if I move from X to X plus H, then the amount that the potential increases in that, it's upper bounded by sort of drawing the tangent to u at that point with a bit of slack that is encoded by this psi. Okay, so if you think that the Hessian of u is uniformly bounded above in operator norm, this psi can just be quadratic. It's L times h squared, where L is the Lipschitz constant. So under this assumption, which is quite easy to verify in various scenarios, you can get this very nice lower bound on the acceptance rate out of any given state. So it's uniform in X, just in terms of this integral against the Gaussian random variable. Okay, so that's true for any step size, but it's only useful for small enough step sizes, right? And so given a specific sort of gauge function C, the idea is you will tune your step size sigma as a function of the dimension and the smoothness function to stabilize the acceptance rate to be at least a quarter or something like this, right? The quarter is a bit arbitrary, but it does sort of match practice. And that's something which you can do in 5 minutes by yourself, for sure. Okay, so if we have a smoothness condition on the potential, we can lower bound the acceptance rate, we can upper bound the rejection rate, we have our close coupling condition, and we're in business. So now we can, I've been in the mines sort of proving things for you, and now we can get out and start paying off, right? So now we want to obtain explicit bounds for the random walk metropolis algorithm. And there's a very nice division of labor that comes up, that there's sort of two parts of the problem that are largely separate to one another, right? You write down the target pi, and you know that one thing you need to know is the isoperimetric profile of pi. And so you find someone who can do that for you. You go check the literature, you see what Emmanuel Millman or anyone else has done to try and estimate these isoperimetric profiles, and then that tells you how you're going to bound this integral down the bottom, right? Separately, you need to understand the smoothness properties of u, and so you get in touch with someone who, maybe they're interested in optimization and minimize methods or something like this, and they get a nice bound on the smoothness behavior of u, and they tell you, yeah, if you want to lower bound the acceptance probability, you'll have to scale your step size like this, right? Those are independent of one another, and you get those estimates as sharp as you can, and at the end of the day, you multiply them together, and that's your mixing time bound as written at the bottom. Okay, so this is conceptually very nice. The two things that make sampling hard with the random walk metropolis are how bad is the target itself, and how well have you chosen the step size, and there's not really much magic beyond that. Okay. So let's give some examples that are sort of nice model problems where we can understand things pretty well. Okay, so this is the sort of conventional one people would study in this literature, which I would call the sort of well-conditioned log concave case. And so the assumption is that your potential u is strongly convex and has a Lipschitz gradient. So roughly speaking, you can think of it as being that this potential is twice continuously differentiable, so its Hessian exists everywhere, and the eigenvalues of that Hessian are sandwiched between m and l, so they're bounded well away from 0 and away from infinity. So in this setting, the isoperimetric profile is, perhaps unsurprisingly, it's as good as the corresponding Gaussian somehow. Right, you have an isoperimetric profile that's like this isoperimetric profile I wrote down for the Gaussian several slides ago, scaled by m to the 1/2, because that's sort of the natural length scale or inverse length scale. Similarly, because the eigenvalues are bounded away from infinity by L, you can take this regularity function C to be LH squared over 2. Again, that's not very challenging. Having written this down, you can see that if you want to stabilize the acceptance probability, you have to scale sigma squared like 1 over L times B. That will give you an acceptance rate of a quarter, right? And that will give you your mixing time as the condition number, so this ratio of L to M, times the dimension, up to some log factors, which I've suppressed for brevity, right? So this is, for a fixed epsilon, let's say, and then from there, you can kind of predict what happens in an easy way that I won't talk about. Okay, so that's the story. The isoperimetric profile sees the strong convexity. The smoothness tells you how to set the step size, and then you go from there. Very nice. Now, here's another class of model targets that are still log concave, basically, but they let us illustrate a few different things. So let p between 0 and 2. I guess you can think between 1 and 2, but I think you can actually get it down to arbitrarily small if you like. So these are things that look like LP norms raised to some power alpha. Okay, so these are sort of reasonably symmetric problems. In the case of alpha equals p equals 2, that's sampling from a Gaussian, right? And following the analysis on the previous slide, you will get a mixing time that's like the dimension up to log factors. And I should say, relatively elementary considerations let you show that you should scale the step size sigma like d to the -1 over p. That's sort of how smooth the P norm is in something. Now, if you stick to P equals 2, so we still have spherical symmetry, but we take alpha between 1 and 2, so we have slightly heavier tails, but still sort of exponentially decaying. You could call this a spherical superpan distribution, right? Here you get a mixing time that's like d to the 2 over alpha, right? So if you have a sort of Laplace type target in high dimensions, the mixing time is like d squared. If you have a to the 3 halves, then you get d to the 4/3 and something like this. So you sort of smoothly interpolate in the mixing time. And then moreover, if you change the roughness of the target by varying the P as well, so sort of LP type superpan, you get a mixing time that also increases as you send P to 0, right? So you somehow what's happening here is one factor in the mixing time is coming from how well concentrated the distribution is, how confining the tails are. And another one is coming from the roughness, you know, the price that you pay for having used a small step size, if you like. Nearly done. So we can also do heavy-tailed targets, right? In this case, one thing that shows up a lot more is the dependence on the initialization is much more stark, okay? So if we focus on sort of product form targets, if I do a product of Cauchys, let's say, or generalized student P's, if you like, you get a mixing time that is polynomial in the dimension if this initialization is very good, let's say. But generically, this factor delta naught is somehow exponential with the dimension. And so you see that unless you initialize a heavy-tailed sampling problem very well, you will pay a price for it in the complexity. Nevertheless, for a warm start, you're polynomial in D and 1 over epsilon, so things are not terrible. But indeed, the problem is harder, right? Similarly, if I take U naught to be sort of quasi-polynomial, then we only have a log factor here, right? We have this log D delta naught on epsilon. That whole thing will still be sort of fully polynomial time in D and epsilon, but you will again see this price of having heavier tails, let's say. I think that's a very interesting methodological problem to think about is how do we initialize well for heavy-tailed problems using things like, you know, annealing and whatever one might consider. Moreover, you know, we can do some analysis outside of the product form setting for these multivariate student P's, where again, you can get a sort of nice explicit convergence rate bound, which is very good when you're initialized well, you pay the price you'd expect otherwise. So this is something, you know, maybe it's obvious to people, maybe people haven't thought about it very much, but indeed we see that the initialization hurts you a lot more with heavy tails. And so maybe you do a change of variables, maybe you change your kernel or something like this, but yeah, you can pay a price. Okay, so I'll just give some takeaways. So yeah, the plan for today's talk was to sort of give a bit of an introduction to isoperimetric problems for probability measures and give some intuition for why they tell you something about Markov chain Monte Carlo algorithms, and specifically about the Random Walk Metropolis. So the way I largely think about the Random Walk Metropolis these days is that it's not so different from the Langevin diffusion. It's very different in some ways, but in terms of its large-scale behavior and how it mixes to equilibrium, there are many similarities that you can understand very well through sort of harnessing these isoperimetric techniques. Yeah, we've taken the approach where we try to do a non-asymptotic analysis where we get a really firm understanding of what's happening for various model problems. You know, of course, they're not necessarily the most realistic from a statistical point of view, but we sort of understand, okay, the difficulties really are how small is the step size and how is the large scale sort of concentration behavior of the target. And so there's this sort of nice local global decomposition where if you can solve those two problems, you know what there is to know. Okay, I'm done speaking and happy to take questions and discuss things. Thank you.